Hey class, welcome back and welcome to chapter 10. So in this chapter we're going to be diving into rotational kinematics. So we're really starting now in chapters 10, 11, and 12. We're going to really be almost repeating everything that we did at the beginning of the semester, but doing it all for rotational motion. So if you remember at the very beginning of the semester we learned about kinematics, motion, right? We're going to now look at rotational motion, rotational kinematics, rotational kinematic equations and variables. Then we went into looking at forces, right? Well, for rotation, we're going to look at what happens when there's a force causing something to rotate, which we refer to as a torque. We also talked and learned just recently about energy, kinetic energy, potential energy, right? We're now going to look at how work and energy relate to things that are rotating. So, and we'll even get into rotational momentum as well as we progress through these next few chapters. So really, everything that we've done so far, we're now repeating, but applying it to rotational motion. So in some ways, these next few chapters are really nice because they're almost a review of things that we've already done and processes we've already learned, but at the same time, be prepared because it's a little bit quick as we take on all these new ideas relatively rapidly, since so much of it is almost review or very similar to what we've done in the past. So let's do a quick review to make sure we remember where we came from or where we covered back in chapters 2 and 4 really. So when you have motion, right, you start with the coordinate axis. If you have one-dimensional motion, you have the x direction, right? Displacement was just the change in position, the final minus the initial. Velocity was the change in position with respect to time. And so velocity was both speed, how fast you're moving, and in what direction, because it's a vector quantity, right? So average velocity was change in x over change in time, and instantaneous velocity was just the derivative of x with respect to time, right? And acceleration is just the rate of change of velocity, okay? So once again, it's a vector quantity. It has magnitude and direction. Average acceleration is just change in velocity over a change in time, and the instantaneous acceleration is just the derivative of velocity with respect to time, or the second derivative of position with respect to time. So as I mentioned at the beginning, we're now going to relate these same ideas to rotational motion. So instead of having position, velocity, and acceleration, we're going to be dealing with rotational equivalents of each of those. All right, as we start to think about direction, we're going to have to think about how we can define direction for something rotating. If you have an object that's rotating around, it seems like its direction is constantly changing, right? It's moving up, left, down, right, up, left, down, right, all the time, constantly changing. So how do we define direction and coordinate systems as we're dealing with these sorts of objects? So to kind of introduce you just to how cool rotational motion can be and how much we see in the natural world, both rotational and translational, so that's like linear motion, rotational and translational motion together. This is just a really cool robotic arm that was created to play ping pong, super finely tuned, and really quite amazing in its ability to move and its ability to react. So you can see here, it's able to move left, right, up, down, forward, backwards, and also rotate the paddle in various different ways, rotating and changing its axis of movement over and over again. So again, this is probably a little staged of a video, but still quite amazing to see all the different types of motion that can be experienced. So how do we describe rotational motion? Well, as I mentioned, we're going to be redefining similar variables that we've already seen as they apply to rotation. So we're going to have angular rotation or angular displacement. We're going to have angular velocity or rotational velocity. We're going to have angular acceleration, so the rate at which it's accelerating in an angular way or in a rotational manner. Then instead of force, we're going to have torque, which is a force that causes something to rotate. We're going to be dealing with angular momentum a little bit later. We're also going to introduce something known as rotational inertia, a super important topic, super important idea, which is really inertia, right? It's the amount of inertia or resistance something has to rotation. Just like mass was the resistance something offered to linear motion, it's the resistance something has to rotational motion. It depends on mass, but other things as well. So we'll learn about rotational inertia and rotational energy. All right, so we're going to be thinking about all these different types of motion because, for example, if you think of an airplane, right, it really has a lot of degrees of freedom, directions it can move. It can go up, down, left, right, but then it can also rotate along this roll axis, it can rotate along the pitch axis, and it can rotate around the yaw axis, right, or the X, Y, and Z axes. So there's really 6 degrees of freedom there in its ability to move. So as you'll see, things can get quite complicated rather quickly. And those of you going into mechanical and civil engineering, you'll get to dive into some of those ideas in greater depth in classes like statics, and especially in dynamics. You'll be dealing with these different degrees of freedoms once you've taken more math and have additional math tools in your tool belt. All right, so let's go through and kind of quickly define the different variables we're going to see. So just like we had linear displacement in chapter 2, for something going through a rotational manner, we're going to have angular displacement, which is just the final angular position minus the initial. So not real tricky, very straightforward. And again, just to drive home, as we've talked about in the past, we define counterclockwise as positive. So here, this angular displacement, delta theta that we see, would be a positive angular displacement as a result of it moving in the counterclockwise manner. All right, so again, angular displacement is the amount that it rotates through the angular displacement it occurs in a given period of time. And so with angular displacement, we still are going to be dealing with vectors. So when you ask, hey, what's the direction of my angular displacement, since it's constantly changing where it's pointing in space, well, the direction is actually about a given axis. So this angular displacement of delta theta is about the axis running through the center of the CD in this image. Okay, so the direction is actually positive, since it's counterclockwise, about this axis. So the way we define direction gets a little trickier. It's either positive or negative about a given axis. And you're going to see, because physics is so awesome, we use radians. Because physics is so rad, we're going to use radians as our units for angular displacement. And you'll see why in greater detail later on. It becomes really important for us to use radian. So that's angular displacement. Moving on, I just want to, again, drive home belt and suspenders. Make sure you understand that any counterclockwise rotation is going to be defined as positive. So again, this would be delta theta here would be a positive angular displacement. If it's moving, it has a positive angular velocity, which we'll get to in a minute. About, in this case, it would be about the z-axis. So you have positive delta theta about the z-axis, whereas here, where it's clockwise motion, it's going to be a delta theta that's negative about the z-axis, because it's the z-axis going into the page in this slide. All right, so again, don't forget when we're talking about angular displacement, we want to use radians, because radians are a direct ratio of the radius of your circle to the circumference of the circle. So the radians, when you're using radians, the angular displacement is a direct ratio of the arc length, which is the distance covered along the circumference, divided by the radius. That's why we use radians, because it's relating the radial distance to the circumference distance, or the arc length, or the perpendicular distance. Okay, so don't forget, radians is just arc length s divided by the radius r, and we know that there's 2 pi radians in one full circle, so 2 pi radians equals 360 degrees. So keep in mind, 2 pi radians is one full circle. It's a bad joke that I've made in the past when you tell somebody, hey, I'm coming over for Thanksgiving, I'm going to make 2 pi, haha, as a joke, because I'm making 1 pi, but it's 2 pi radians. Yeah, it's not funny when you show up with 1 pi instead of 2. All right, so here's a quick example for you. Sorry, I make math jokes to myself and laugh at them, so enjoy. All right, so synchronous satellites, all right, geosynchronous satellites, ones that stay over the same exact place on the Earth, as we discovered and calculated earlier in the semester when we were looking at uniform circular motion. They orbit, if you have a circular orbit, at a distance away from the center of the Earth of 4.23 times 10 to the 7th meters. Now, if you had a telescope or something, you're looking at a satellite or somehow tracking its motion, and you realize that the satellite goes through an angular displacement of 2 degrees, right? And notice it's degrees, not radians, 2 degrees. what is the actual arc length distance that it's traveled? How far has it moved from when it started to when it finished its 2 degrees of motion? So 2 degrees is a tiny, right, out of 360, not very much. 1/180th of a full circle is all that it's gone. What is this arc length distance S? Pause the video, give it a go, and see if you can figure it out. All right, so hopefully you paused, hopefully you gave it a go, hopefully you figured it out. Let's do it together really quickly. So again, remembering theta in radians is equal to arc length over the distance. So first we need to convert our 2 degrees to radians. So we know that there's 2 pi radians and 360 degrees. So multiplying by that conversion factor, our angular displacement is 0.0349 radians. And solving, arc length equals theta times r. So theta times r, multiply those out, and you get an arc length of 1.48, times 10 to the 6th meters, or about 920 miles, is the distance it's covered during that 2 degree angular displacement. One thing to notice that confuses people here, boom, Boxworthy. One thing that confuses people, notice we're taking meters and we're multiplying by radians and we're getting units of meters. What? Right? This is one of the most confusing things that people run into. But as I mentioned, remember, radians are really just a ratio of the arc length to the radius, right? They're really just a ratio transforming your direction from the radial direction to the circumference direction or the perpendicular direction, right? So when you multiply by radians, you're changing the direction of the meter orientation, but you're keeping and preserving those units of meters. So you got to be really careful. I don't ever want to see somebody give me units of meters times radians on a problem like this. It's just meters. The radians are the ratio that transform the direction. All right, so just kind of a cool observation I made about the amazing way that God has created the world. One thing you might have noticed, I recently had the joy of getting to observe a total solar eclipse, something I'd always wanted to see, and one came very near to Oregon recently, and I drove just a few miles south and was able to watch it. It was awesome. But anyway, the reason that total solar eclipses occur, and they occur only rarely, is partially due to the fact that the diameter of the sun is almost exactly 400 times the diameter of the moon. And in addition, not only that, but also by coincidence or by God's amazing design and creation, the sun, the distance from the sun to the earth is almost exactly 400 times the distance from the moon to the earth on average. So the sun to the earth is 400 times the moon to the earth, and the size of the sun is about 400 times the size of the moon. And so what this means then is that when the two objects line up perfectly, the sun and the moon, their distance or their size as viewed from Earth, their angular displacement that they each take up in the sky, is almost identical. And so what this means then, if they perfectly line up, the moon will be able to just barely block out the sun. If the moon was any closer to the Earth or any smaller, or if the sun was any closer to the Earth, you would never get to see a total solar eclipse. Now, if the sun was further or the moon was much bigger or much closer, then we'd see solar eclipses all the time and there wouldn't be anything special. But this perfect setup means that you only get to have a solar eclipse once or twice a year and only in a tiny, tiny portion of the Earth. So I'm someone who's been into physics for a very long time. This past year was the first time I was very close to any total solar eclipse. Definitely the first time I was within driving distance of a total solar eclipse, and he'll be the last time for quite some time unless I happen to move or take a vacation. The next one, I have a friend who's planning a trip down to Chile to go observe a total solar eclipse. That gives you an idea of how rare they are. So it's really quite amazing that their radial distance, their angular displacement in a sense, is the same as viewed from Earth, which allows you to have this perfect amount of covering. And the amazing thing is the moon's distance from the Earth actually varies slightly because it has a slightly elliptical path. And so that means that when it's closer to the Earth, you get a total solar eclipse. It'll block out the sun perfectly for just a few people who happen to fall under the darkest part of the moon's shadow, the umbra. But if the moon happens to be on its further point away from the Earth when it lines up perfectly with the moon, then it's actually not even big enough to completely block out the sun. You don't get a total solar eclipse. Instead, you get what's known as an annular solar eclipse, where you can just see a tiny bit of the sun all around the moon, and it's not nearly as dramatic of an event as a total solar eclipse. So that's how close it is, how perfectly sized everything is within our solar system. All right, so we've talked about angular displacement. That's fun and good, but we need to move on, right? What about angular velocity, acceleration, and so on? So we're going to talk now about angular acceleration. Now, angular velocity, and then angular acceleration. So angular velocity, as you might have guessed, just like linear velocity, is just displacement over time. But now you have angular displacement over time. So average angular velocity is just your change in angular position, also known as angular displacement, divided by the change in time. And the units, as you probably could have guessed, are just radians per second. And this funny curvy looking W you see over here is just the Greek letter omega. So you notice we had X, V, and A, all normal English letters, right, for displacement, velocity, and acceleration. Now we're going to have theta, omega, and alpha, all Greek letters to represent angular displacement, angular velocity, and angular acceleration. So that's average velocity. So let's just do kind of a quick example here. So here's a gymnast swinging around the high bar. All right. So let's say he swings around in the way shown here. You can see the picture. All right. And during a time period of 1.9 seconds, he goes through 2 revolutions. What is his average angular velocity during that time? Pause it, do a quick calculation. So if you did your quick calculation, first of all, tricky part that a lot of people miss here, the angular displacement is -2 revolutions because he's going clockwise, right? I got some of you on that one, I know I did. All right, but first you need to go from revolutions to radians because we want units of radians. So there's 2 pi radians in each revolution. Multiplied by 2, we get 4 pi, or -4 pi radians really, which is the equivalent to approximately -12.6 radians. And it's just displacement over time, so we get -6.63 radians per second. Boom, box-worthy. All right, now that's the average angular velocity, but we want instantaneous, right? So the instantaneous, we just take the limit as time approaches 0, taking the limit, we will just really redefine omega, the instantaneous angular velocity, as being the derivative of angular displacement with respect to time, just like we saw back in chapter 2. And then lastly, just to bring it all full circle, angular acceleration is just change in angular velocity with respect to time. So average angular acceleration is just delta omega over delta t. Instantaneous is just the derivative. And again, this A looking letter is just the Greek letter alpha. All right. And once again, we're still using radians, right? So now that we're having an acceleration, it's radians per second squared. So quick example problem for you all here, all right? Here's a jet engine. It's going to be revving up, okay? So let's say that these fan blades, they're rotating at an angular speed of -110 radians per second, because they're going in a clockwise direction. Now, the plane's getting ready to take off, so it needs to get those blades spinning faster. They want to get it up to a speed of -330 radians per second, an angular velocity, I should say, of a -330 radians per second, and this will need to occur in 14 seconds. Based on that information alone, what is the angular acceleration? Let's assume that it's constant, or really just say that we're finding the average angular acceleration. Do the math. Final minus initial, which is negative, right? So negative and a negative, you end up adding. So you have -220 radians per second divided by 14 seconds, and you get approximately -16 radians per second squared. So both of these examples are on the simpler side. I'll have some more complicated sample problems in separate videos, just like we've done in past chapters. All right, so now let's put all this together with the things we've already learned back in chapter 2 and 4. So in chapter 2, we had 5 kinematic variables when we found our equations of motion, right? We had displacement, acceleration, final velocity, initial velocity, and time, right? Well, now look at this. In rotational motion, we have similarly 5 variables. We have angular displacement, we have angular acceleration, we have final angular velocity, initial angular velocity, and elapsed time. So guess what? Just like back in chapter 2, we get to have different equations of motion. So you'll see that we have very similar equations of motion to what we had before. Final angular velocity equals initial angular velocity plus angular acceleration times time. Angular displacement equals 1/2 initial angular velocity plus final angular velocity times time, just like we've seen before. And same thing with our other equations. Angular displacement is just going to be represented by theta in these two, but you could also have theta minus theta initial for angular displacement. So the equations of motion look just like our other ones, replacing all of our English letters with Greek letters, and you have really the same equations that we're going to get to use over and over again. So it's really just a repeat of what we've done in the past. Again, just kind of showing you these equations side by side. Each of the different equations of motion that we dealt with earlier are now being repeated. So much of what we're doing now is, again, just a repeat of things we did quite a bit back in chapters 2 and 4. If you get confused why I keep saying 2 and 4, 2 and 4 were both about kinematics, right? Chapter 3 was the vector chapter in between, which enabled us to do two-dimensional motion. Cool. All right, so what are you going to do in these problems? Well, you're going to follow the same problem-solving strategy that we've done in the past. Again, don't forget, trust the process. Follow the process. So you start with the drawing. Make sure you have a good, well-done drawing. You look at your direction of rotation, right? Define positive and negative, counterclockwise versus clockwise. Write out a list of your knowns and unknowns, figuring out which kinematic variables you have, which ones you're looking for, and then try to set up which of the equations is most likely going to be useful. Each one is missing a different variable, so try to isolate just one single variable you need. If not, you might need to select multiple equations and set up solving multiple equations for multiple unknowns. Once you do that, try solving and see whether or not your answer makes sense. So here's a quick example that we're going to be doing for you all. It's kind of funny, blenders. I don't know how many of you have used a blender, but especially those older blenders, they have those like super arbitrary buttons. You know, it's like chop and puree and blend and obliterate and annihilate. Like, I don't know what those little buttons mean exactly, but let's use an example. So here's two buttons, puree and blend. What the difference is, we don't quite know, but that's okay. So there's puree and blend. Let's say that it's your blades are whirling at the puree setting, and you somehow quantify the angular velocity as being a positive 375 radians per second. All right, you decide you want to kind of pump things up a little bit, and apparently blend is above puree. So you hit the blend button, and the blades accelerate. Okay, so let's say that they experience a constant angular acceleration of 1,740 radians per second squared. And during this acceleration period, they rotate through 44 radians. With that information, I want you to tell me what is the final angular velocity that the blades have. For fun, you can also calculate the time it takes if you want. But the question just asks for the final angular velocity. Give it a go. Pause, go. All right, so I'm going to get started. I have my picture over here. I define my axis of rotation. I notice everything's going counterclockwise, so it's positive values. I make my list of variables. I'm going to define my initial angular displacement as 0. It was already moving, right? It had already gone through. But the moment the acceleration starts, I'm going to reset my counter and define that as my 0. So I have 0 as theta initial, positive 44 radians as theta final, alpha is 1,740 radians per second squared. Omega final and time I don't know, and omega initial is also given. So I list my variables, and then I look at my equations of motion. There's one of them that does not depend on time. Since I don't know time, I want to use the equation that does not involve time. So I look here, oh yeah, I know everything in this equation other than omega final, which is what I want. So I take the square root of both sides and plug in 0 for theta initial, plug in my values, and I get a box-worthy answer of 542 radians per second. Boom, box-worthy answer. So again, see the process, very similar to what we've done in the past. So now the next thing I want to kind of briefly dive into, and then here in a few minutes we're probably going to cut and do the second half of this chapter in another video since there's so many different topics we're revisiting. But now I want to think a little bit about how do we relate this rotational motion stuff to the translational motion we did back in earlier chapters. So let's say, imagine you have somebody that's moving here in rotational motion. We're going to just model this as, various figure skaters or some sort of skaters are going to be going around in a circular motion. All right, so they're moving with some tangential velocity. Their tangential velocity, just so you know, is really just their linear velocity at a given moment. The reason we call it tangential is because it's tangential to that radial motion. All right, so here's the radius of their circle, right? This line represents the radius. The tangential velocity is tangent or perpendicular to that direction. So as the radius value rotates, the direction of that tangential velocity constantly changes. Okay, so I want to relate tangential variables to angular variables. How do you think they rotate? Maybe pause it, maybe sketch out some equations. What do you think the connection is between what we just were learning and the tangential velocity or acceleration or even displacement? So let's think about this. Well, tangential velocity, let's assume for now we're just dealing with a constant motion. So tangential velocity is just going to be the distance, s, right, the arc length distance over time, right? And if you remember, s, arc length, is just equal to theta times the radius, as long as you're in radians, right? Theta times r is arc length, so you can redefine tangential velocity as being r times theta over t. Well, what is theta over t? That's just omega. So tangential velocity at any given point in time can just be defined as being equal to r times omega. Pretty cool, right? So r times omega, as long as you're in radians per second, gives you the tangential velocity. Now let's look at the same thing for acceleration. Now acceleration is a little tricky, right? You can have centripetal acceleration, which we already learned was v squared over r, right? So we already have tangential, or excuse me, we already have radial or centripetal acceleration. Now let's find tangential acceleration. What if you're spinning something and it's going faster and faster and faster? It's going to experience a linear type acceleration where that tangential velocity is increasing, right? So not only will the rotational speed be increasing, but the tangential speed will also be increasing if it's rotating faster and faster. So acceleration is change in velocity over change in time, right? If we're assuming average or constant acceleration. And so velocity, tangential velocity, we already said is r times omega. We already found that out. So r times omega final minus r times omega initial over t is tangential acceleration. So redefining this, factoring out the r because the radius is constant, now we can say, hey, look, omega final minus omega initial over time, that's just our angular acceleration. So we can redefine tangential acceleration as being equal to the radius times the angular acceleration. Again, this is provided that alpha is in radians per second squared. So just as a reminder, as I mentioned earlier, we know that centripetal acceleration is v squared over r, right? V just being the tangential velocity. So again, we can make the substitution of what we discovered earlier. The tangential velocity is r times omega. Plugging that in, we can redefine centripetal acceleration as r times omega quantity squared over r. Canceling out one of the r's, we find that centripetal acceleration is r multiplied by omega squared. And to find the overall total acceleration, right, if an object is moving in non-uniform circular motion, that means that it will still have a centripetal acceleration, but now it also has a tangential acceleration while it's speeding up or slowing down. And so its overall total net acceleration would really just be the vector sum of those two components, noting that centripetal acceleration and tangential acceleration are always perpendicular to one another. The overall acceleration is just going to be equal to the square root of a t squared plus ac squared. Pretty cool, right? Now, keeping in mind, don't forget how we define positive and negative. One way to know if you're dealing with positive or negative, if you ever get confused, is using what's known as the right-hand rule. Okay, so with the right-hand rule, if you curl your fingers in the direction of motion, all right, your thumb gives you really the direction of your vector that you're dealing with. So if you're looking at, for example, angular velocity, if I curl my fingers in a counterclockwise manner, look, I get a thumbs up, positive angular acceleration. Now if I curl them in a counterclockwise direction, that's going to give me thumbs down, so that's a negative angular velocity or angular acceleration, depending on what type of motion you're dealing with. So the right-hand rule we'll talk about more later in this class, but is one way to help think about direction. All right, so how does the forward speed of an object like a car or something that has wheels that are rotating, but it's also moving forward, how does the forward speed relate to the rotation of the tires? Interesting question, right? So here's a car, here's its tires that are going to be rotating. How does the linear velocity relate to the rotational velocity of these cars? Well, we know for the tire, if you notice, look, as the tire rotates, the distance covered by the tire from some point A to some later point B, that distance is really just the arc length covered by the tire, right? And so really what we find, if we combine these ideas of what we were just learning, if we combine these ideas of what we were just learning, since the arc length distance covered by the outer edge of the tire is the same distance covered by the car, what that then means is the tangential velocity of the outside edge of the tire is the same as the forward linear velocity of the car. The tangential acceleration of your outer edge of your tire is equal to the acceleration, the linear acceleration of the vehicle. So if something is rolling without slipping, important, it must roll without slipping. If this tire is just spinning out, then you can't relate the two. But if it rolls without slipping, the tangential velocity and tangential acceleration of the tire at the outer edge, so at the furthest radius, is equal to the linear velocity and acceleration of the vehicle. So one last example problem, and then we'll wrap this video up. So imagine you have a car that starts from rest. For 20 seconds, it's going to have a constant linear acceleration of 0.8 meters per second squared. It has tires with a radius value of 33 centimeters or 0.33 meters. What is the angular displacement of the tire during this period of acceleration? Ready, go. So, sneaky, right? We want angular displacement, but I gave you only linear variables. They're directly related though, right? Acceleration is alpha times r. The linear acceleration of the car, which is the tangential acceleration of the tire, equals alpha times r. So alpha is just acceleration over r. I can then solve for alpha by taking acceleration dividing by r. Boom, I get 2.42 radians per second squared. So that's my angular acceleration, but if you notice in my picture, I'm rotating clockwise, so while that's the magnitude, it's in the negative direction. Oh, sneaky. We're told we start from rest, so omega initial is 0, and our time is 20 seconds. We're given that at the beginning, so time is the same for both rotation and translation. Lastly, we don't know omega final, and we don't know theta final. We do know theta initial is 0, and we don't care what omega final is. All we care about is theta final, the angular displacement, which is what we're asked to find. So we choose our equation of motion that does not depend on omega final since we don't care about that. Then we observe we know everything, we know except theta final. We know omega initial 0, omega initial 0, we know theta initial 0, we know alpha and time. So we plug in our values for that, 0 plus 0 plus 1/2 at squared, do the math, and we find a box-worthy answer that theta is equal to negative 484 radians. Hopefully that's what you got. And yeah, I'm going to stop here. You're going to get lots of homework practice on applying these kinematic equations to rotational problems and relating translational and rotational motion together. I'm going to pause now or stop this video. We'll continue with part B of this chapter 10 a little bit later, where we dive into looking at kinetic energy, torque, and some other rotational variables. Have a box-worthy day.